So next, let's look at example 8. Here, a small town has two gyms, A and B. At the end of each year when memberships are up, members of Gym A have a 35% chance of switching to Gym B and 65% of them stay at A. Similarly, members of Gym B have a 62% chance of switching and 38% chance to stay put. Notice, by the way, that these bits of data, the proportions that stay, those don't necessarily need to be given to you in the prompt. Because if they have a 62% chance of moving, then that means that 38% of them are going to stay put, assuming that we aren't losing gym memberships. So we don't technically need to include that full percentage, like the complementary percentage, if these are the only two possible states. So we want to know if members are initially split evenly between those gyms, what's the distribution of members after 2 years? So for this, we need to write down the transition matrix, and then we'll start talking about the states. So I'm going to use the natural ordering here. So I'll have the states ordered as A and B. We have a 65% chance of going from A to A, a 35% chance of going from A to B, a 62% chance of moving from B to A, and therefore a 38% chance of moving from B to B. So this is our transition matrix, and now what we want is V2. We want the state at time 2. We know the initial state. The initial state is that the members are split evenly between the two gyms. So in other words, 50% of customers are at state A, and 50% of customers are in state B. So this is our initial state. Next, we'll compute the state at time 1. For that, we're just going to take V0 and multiply by the transition matrix. And if you compute this product, which I would recommend that you do in just like a calculator, then what we end up doing is we get, 0.635, and then 0.365. And by the way, maybe this is a good time to mention, if you're confident with your matrix multiplication skills and you compute that the first entry is 0.635, then you can use the trick that I described at the end of the last video to generate this other entry pretty quickly. So if I know that this is a 0.635, then I know that if I want these two entries to add up to 1 in total, then for each of these digits, I want the sum of the corresponding digits in the other, or sorry, I should say the sum of this digit and the corresponding digit in the other entry to add up to 9. So this first entry would have to be a 3, and then the next entry would have to be a 6. And then for the last entry, we want that to add up to 10. So we would have a 5 here. So that's a quick way of generating the complementary entry. However, it's also okay to just fully do the matrix multiplication, and then you have a way of checking your answer. Because if these two things did not add up to 1, then you know that something is wrong. So this is state at time 1, and now if we want the state at time 2, we can just take the state at time 1, which we just found, and we can transition again. So I'm going to take this and I'm going to multiply by the transition matrix one more time. And when I compute this product, what I end up getting is a 0.63905. And again, I could quickly generate what the complementary expression needs to be, or I can just compute it explicitly. Either way, this is what we end up getting. So this is the distribution after 2 years. We would have 64% roughly of all customers would live at Gym A, and 36% of all customers would live at Gym B after 2 years. So next, let's look at example 9. So here, what we have is a probability of having bad weather 2 days in a row, which is 20%, and the probability of having good weather twice in a row would be 60%. Now, this is a little bit ambiguously phrased, so I think maybe let me make it slightly more technical. What I mean by that is just that if you have bad weather on one day, the probability that you'll have bad weather the next day as well is 20%. And given good weather today, the probability that you'll have good weather tomorrow is 60%. So now we want to draw the transition diagram. So I'm just going to put G for good weather and B for bad weather. So here's our transition diagram. And now what we know is that the probability of having bad weather twice in a row is 20%. So if we had bad weather today, there's a 20% chance that we also have bad weather tomorrow. Now, that's enough information for us to determine the weight of this arrow, because we're either going to go from B to B or from B to G. And if there's a 20% chance that we stay at B, then there must be an 80% chance of going to the other state. Similarly here, if we're going from good to good, there's a 60% chance, and therefore there's a 40% chance of transitioning from good to bad if we had good weather today. So that's our transition diagram. Now we can write down the corresponding transition matrix. Now, when you write down the transition matrix, it doesn't matter which order you put the states in as long as you're consistent between your rows and your columns. So I'm actually going to switch this up a little bit. I'm going to put the bad news first. So we'll put bad, good, and I'll do the same thing here. I just have to be consistent in my ordering. So this is a perfectly good transition matrix, but you need to make sure that your transition matrix, if you choose the ordering bad and then good, that both the rows and the column order match, and also that for the states, we would have the same ordering. So we would have bad and then good. So as long as you're consistent in whatever ordering you choose for your states, then everything will work out fine. So here, if we want the transition matrix, we know that from bad to bad has a 20% weight, and therefore from bad to good has an 80% weight. And similarly, good to bad has a 40% weight, and therefore a 60% weight goes to good to good. And that's our transition matrix. And then lastly, it says, suppose that the forecast says there's a 40% chance of rain tomorrow, estimate the probability of having bad weather on the following day. So here we're given the initial distribution. So maybe let me write it this way. I'll say we're given the state at time 1 because it's tomorrow's forecast. And what we want is V2. So we want the state 2 days from now, but we're given the state 1 day from now. And the state, remember, has to match the ordering that we chose. So this would be bad and then good. There's a 40% chance of rain tomorrow. So that means there's a 40% chance that the state will be bad tomorrow. And therefore, there's a 60% chance that the state will be good tomorrow. So if this is our forecast for day 1, or for 1 day from now, then we can use our model to generate a forecast for any future day that we want. But in particular, we can find the forecast for the next day. If I want the forecast for the next day, I just need to take state 1 and take 1 time step. So I'm just going to take the 0.4, 0.6, and multiply by our transition matrix, 0.2, 0.8, 0.4, 0.6. This one might be a good one to compute by hand if you need some practice working with decimals, but it's also always okay to just type these individual computations or the entry computations into a calculator. So you could just type in 0.4 times 0.2 plus 0.6 times 0.4, and that would give you this first entry, which ends up being 0.32. And therefore, this next entry would have to be a 0.68. And this is our probability of having bad weather 2 days from now and having good weather 2 days from now. So if we wanted to interpret this to finally answer the question, it says estimate the probability of having bad weather on the following day. The probability that we get as our estimate is 32% chance. So 32% chance of bad weather the following day. Now, maybe I should mention something about this before I end the video. You can use Markov chains to do some sort of elementary weather prediction like this if you wanted to, if you knew the statistics of these transitions in your area. However, well, maybe I should say this. Actual weather modeling is a stochastic process. So the stochastic processes that I defined up at the beginning of this lecture, those sorts of models do include weather prediction. However, actual weather prediction, or maybe I should say actual weather modeling, is not a Markov process. It's not a Markov chain because it's not memoryless. In other words, the state of the weather tomorrow is not just going to depend on today's weather. If it only depended on today's weather, then it would be memoryless. It doesn't care about what the weather was yesterday or last week or whatever. Then it would be truly memoryless, and then we could use this model to get accurate weather predictions. But obviously, the weather doesn't just depend on what the weather was today. Instead, the weather depends on its entire past. So it depends on what the weather was yesterday and last week and so on. And therefore, because that is not actually a memoryless process, this is not going to be a very accurate model day to day. However, it will get sort of long-term predictions correct in the sense that it will understand the correct proportion of bad days to good days in some vague sense that I don't really want to define.